conference will now be recorded.
Good morning, all. Today I'm going to give a demo on DFT, which is Design for Testability. Could you please confirm if my voice is audible and if my voice is clear?
Yeah, it is audible. Yeah.
Okay. So before we go into what is called as DFT, we'll first try to understand what is VLSI. So VLSI stands for Very Large Scale Integration. VLSI stands for Very Large Scale Integration. So it is implementation of million transistors in a small area. So goal of VLSI. Goal of VLSI means if a particular company is designing a chip, then they will be having some primary conditions that has to be met. So that is what is the goal of VLSI. First one is high performance, ensuring faster processing and low power consumption. So optimizing power usage to extend the battery life, and low area or minimal area. So reducing chip size to achieve compact products. And this is how our chip will look like after manufacturing. Next, we'll try to understand ASIC flow. The full form of ASIC is Application Specific Integrated Circuit. So which means the IC which we are designing, it will be specific to a particular application. For an example, a modem chip, it cannot be used as a chip which is responsible for deployment of airbag in your automobile. A modem chip, it cannot be used as a chip which is responsible for deployment of airbag in your automobile. Okay, so that is what is called as application specific integrated circuit. The IC which we are designing, it will be specific to a particular application. So ASIC flow means it actually gives the steps which we need to follow for designing a particular chip. So these are all the steps which is involved in the process of chip design. So that is what is ASIC flow, the steps which is involved in the process of chip design. So in the upcoming slides, we will discuss about the various steps which is involved in the process of chip design. So the first stage is the design specification stage. Okay, so the first stage is the design specification stage. So based on the application for which we are designing the chip, certain specifications will be decided, like what has to be the speed, how many memory modules, how many processors, how many sensors are required, what has to be the power. So such kind of specifications will be decided. Okay, so based on the application, for which we are designing the chip, certain specifications like what has to be the speed, and then how many memory modules, then processors, sensors are required, and then what has to be the power. So such kind of specifications will be decided. So based on the application for which we are designing the chip, certain specifications like what has to be the speed, how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided. Next, we have the design code stage. So design code stage, so it will be done by the design team. So they will be writing the design code of the chip. They will be describing the functionality of the chip. So the design code which is written, it will be in behavioral model, or data flow level model. Okay, so it will be done by the design team. So they describe the functionality of the chip, they write the design code of the chip. So the design code which is written, it will be in behavioral model or data flow level model. And after that, we have the verification team. Verification stage, it is actually to validate the functionality of the design to ensure that it meets the required specification and performs as intended. So verification, they will be validating the functionality of a design. Functionality of a design to ensure that it meets the required specification and performs as intended.
Excuse me.
Yes.
Like lab section is not there because this class I heard before. So you done this? So I'm asking.
Yes. Today you are from DFT Advanced August
Yes, ma'am.
batch, right?
Yeah,
Yeah.
advanced.
Today lab session is not there. This is a demo session for a new batch.
Okay, because you stopped at case 3, so I was like confused a bit. So then we
Yeah.
have
Okay.
tomorrow, ma'am.
Yes. Tomorrow.
Okay, thank you. Can I leave the section? Ma'am?
Yes.
Okay.
So verification team, they validate the functionality of a design to ensure that it meets the required specifications and performs as intended. And after that, we have the synthesis stage. So during the synthesis stage, what will happen is the behavioral and data flow level model code, it will be converted to structural form, or we can call it as the technology node specific gate level netlist. Okay, so the behavioral model or data flow level model code. Data flow level model code. Okay, so it will be converted into structural form. Structural form, or we can even call it as technology node specific gate level netlist. Technology node specific gate level netlist. Okay, and after that we have the design for testability, that is the DFT. So DFT, it is actually to insert test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. We'll try to understand about this design for testability team in the upcoming slides more in detail. And after that, we have the physical design team. Physical design team, they convert the gate level netlist into layout form. So physical design team, they convert the gate level design into layout form. Gate level design into layout form. And after that, you have the sign off. So in sign off, like we have these 3 steps. So one is static timing analysis, and the other one is physical verification, and the third one is logical equivalence check. Okay, so we have static timing analysis, and then physical verification, and the third one is logical equivalence check. Okay, so static timing analysis, STA, as its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violation. Static timing, STA stands for static timing analysis. As its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violations. And then PV is physical verification. So it is to verify the layout of the circuits. And next is LEC. So LEC stands for logical equivalence check. So logical equivalence check, LEC, it is actually done in order to check whether the final design is logically equivalent to the original design or not. So that is what is LEC. LEC is actually done to check whether the final design is logically equivalent to the original design. So what is the need of doing LEC is, if you see in the process of chip design, our design undergoes a lot of changes in each stage. So first we had the behavioral and data flow level model form of the code. And at the time of synthesis, it got converted into a structural form, or you can call it as a technology node specific gate level netlist. And if you want to go for low power design, then certain special cells have to be added, like clock gating, and then retention registers, level shifters, like that. Some more extra cells have to be added into your design. And then we have the design for test team, where we will be adding our own structures like scan insertion, embed insertion, boundary scan insertions, like that. We will be adding our own structures. So if you see, in each and every stage, our design is undergoing a lot of changes. So that's why LEC is actually done to check whether the final design is logically equivalent to the original design or not. And next is tape out. So tape out means delivering the database to the manufacturing unit. Tape out is delivering the database to the manufacturing unit. Delivering the database to the manufacturing unit. And then you have the packaging and testing. So packaging and testing, it is actually done after manufacturing. Packaging and testing, it is actually done after manufacturing. Okay. So packaging means, so if you see, this complete circle is a wafer and each individual portion will be called as die. So covering this die with a protective layer is called as packaging. And testing, it is actually done to check whether our device is good or not, whether our chip is good or not, whether our chip has any manufacturing defects or not. So that is what is testing. Okay. So this complete circle is the wafer and each individual portion is called as a die. Packaging means covering this die with a protective layer is called as packaging. Testing, it is actually done to check whether our chip is good or not, whether there are any manufacturing defects or not. Okay. So in the upcoming slides, we will discuss more in detail about this verification, design for testability, and then this testing. So all these points, we will have more focus on it in the upcoming slides. So design for testability, that is nothing but DFT. What is DFT? DFT, it is actually to insert test structures in the design. Like we will be adding our own test structures like scan insertion, embed insertion, boundary scan insertion. Like that, we will be adding our own test structures into the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. Pre-silicon stage means before manufacturing. To facilitate, to facilitate means to help the detection of manufacturing defects in the chip. So DFT is to insert test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. Okay. So which means if a particular chip fails after manufacturing, DFT team will be able to tell what manufacturing defect has caused the chip to fail. Okay. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. So how we are able to tell that? You'll be able to understand when we do the course, regular course when we do it, you'll be able to understand. What is the role of a DFT engineer? So DFT is to insert test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. Yes, that is what we had discussed it in the previous slide. DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. Okay, DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. Let's try to understand this with the help of an example. So we had seen two teams. One is the design for testability team and the other one was the verification team. So we'll try to see a difference between those two teams and why both the verification team as well as DFT team is required. So in the ASIC flow, we had seen two teams. One was the verification and the other one was the design for testability team. So what is the difference between a DFT engineer and a functional verification engineer? And why do we need both the DFT team as well as a functional verification team? Let's try to understand with the help of an example. So if you consider a half-added design, just consider a half-added design. So sum is A XOR with B, carry is AB. So whether this is written correctly or not. This is what will be checked by the functional verification team. They will be checking the functionality. So by mistake, if someone writes sum is equal to A plus B, carry is equal to AB. So this will not function like a half-adder. Okay, by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, this will not function like a half-adder. So this is what will be checked by the functional verification team. They will be checking the functionality. Okay, so this is what will be checked by the functional verification team. They will be checking the functionality. Okay, so that is what. Now DFT team, what do we do is we do not check the functionality. We check whether each and every net of the half adder is free of defects or not. So say for example, this is what is our intended design. So sum is A XOR with B, carry is AB. So the A and B of this half adder, it is coming from flops, and then sum and carry of this half adder, it is going to some flops. Now suppose during manufacturing, this A net unintentionally got connected to ground. Unintentionally during manufacturing, A net of the AND gate has got connected to ground. So this kind of things is what will be checked by the DFT engineer. Okay, so this left side one is the intended design. Now during manufacturing, unintentionally, A net of this AND gate has got connected to ground. So these kind of things is what will be checked by the DFT team. Okay, so we will explore more in detail about what is the difference between DFT engineer and functional verification engineer, and we'll also try to understand why we need both DFT team as well as a functional verification team with the help of the next example. So let me just take another example. Like, why do we need DFT team when we have a functional verification team? So let's try to understand with the help of an example. So in this case, say for example, I'm having a design. So where my design is a 10-bit counter with a counter initialization and a counter observation circuit. Okay, in my design, I'm having a 10-bit counter with a counter initialization and a counter observation circuit. Now suppose counter is manufactured with a defect. Okay, suppose counter is manufactured with a defect. So that's why after counting to 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, suppose counter is manufactured with a defect. So that's why after counting to 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so now we'll try to understand what will happen if only functional verification team exists and what will happen if a DFT team exists. So the first case, if only functional verification team exists. So what is the scenario? Scenario is we are having a 10-bit counter with a counter initialization and a counter observation circuit. And suppose the counter is manufactured with a defect. So after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay. So now, if only functional verification team exists, what will happen? Functional team, they test the counter with functional patterns. Okay, if only functional verification team exists, functional team, they test the counter with functional patterns. So in this case, it will take more than 1000 clock pulses. Okay, it will take more than 1000 clock pulses. Okay, it will take more than 1000 clock pulses to tell that the counter is failing. So why is it like that? Why will it take more than 1000 clock pulses to tell that the counter is failing? Okay, so the reason is functional verification team, they check the functionality. Functional verification team. Okay, functional verification team, they check the functionality. Check the functionality. Okay, that is, in this case, what do they check? They check if the counter properly counts from 0 to 1023 because our design is a 10-bit counter. Okay, so that is, they check if the counter counts from 0 to 1023. Counts from 0 to 1023. Okay, so functional verification engineer, they check the functionality. That is, in our case, they will check if the counter counts from 0 to 1023 properly. So now here in this case, what is happening? The counter is failing at the 1000th pulse. Okay, so the counter is failing at the 1000th pulse. Okay, so in this case, the counter is failing at the 1000th pulse. Okay, why? Because at the 1000th pulse only, counter is again counting 999 instead of 1000. Okay, so that is at the 1000th pulse. 1000th pulse, counter is again counting 999. Counter is again counting 999 instead of 1000. Okay, that is at the 1000th pulse, counter is again counting 999 instead of 1000. So that is why counter is failing at the 1000 pulse. So 1000 pulses are required for this. 1000 pulses are required. And some more clock pulses are required for counter initialization and counter observation. Okay, so some more clock pulses are required for counter initialization and counter observation. Okay, counter initialization means in order to bring the counter to the initial state. And counter observation means the output of the counter, it has to be taken to some register and the register has to be read. So some more clock pulses are required for counter initialization and counter observation. So ultimately we can say that functional verification team, it will take more than 1000 clock pulses to tell that the counter is failing. Okay, so if only functional verification team exists, what will happen? It will take more than 1000 clock pulses to tell that the counter is failing. The reason is functional verification team, they check the functionality. That is, they check if the counter counts from 0 to 1023 properly in this case. So counter is failing at the 1000th pulse. So the reason is because at the 1000th pulse only, counter is again counting 999 instead of 1000. Okay, at the 1000th pulse only, counter is again counting 999 instead of 1000. So 1000 pulses are required. And some more clock pulses are required for counter initialization and counter observation. Okay, so that's why functional verification team, they will take more than 1000 clock pulses to tell that the counter is failing. And then functional verification team, they can only tell that the counter is failing. Functional verification team can only tell that the counter is failing. So the reason is because functional verification team, they check the functionality. Check the functionality. Okay. So functionality means in this case, they will check if the counter properly counts from 0 to 1023. That is, check if the counter counts from 0 to 1023 properly or not. 0 to 1023 properly or not. So that is what will be checked. So they will be checking the functionality. That is, they check if the counter counts from 0 to 1023 properly or not. Okay, in this case. So now here in our example, what is happening? In our example, in our case, counter after counting 999, instead of incrementing to 1000, it once again counts 999. So the counter is failed. Okay. So in this case, after counting 999, okay, after counting 999, instead of incrementing to 1000, instead of incrementing to 1000, okay, it is once again counting 999. Once again counting 999. So counter is failed. Okay. So functional verification team, they can only tell that the counter is failing. The reason is because they check the functionality. In our case, they check if the counter properly counts from 0 to 1023. But in our example, what is happening after counting 999, instead of incrementing to 1000, it once again counts 999. So counter is failed. Okay. So this is what. So what is the scenario we are considering? Our design is a 10-bit counter with a counter initialization and a counter observation circuit. So we have considered a scenario. Scenario is, suppose the counter is manufactured with a defect. So that's why after counting 999, instead of incrementing to 1000, it once again counts 999. So now what will happen if only functional verification team exists? So if only functional verification team exists, it will take more than 1000 clock pulses to tell that the counter is failing. And why? That is what I have explained it here. And functional verification team, they can only tell that the counter is failing. Okay, functional verification team, they will only be able to tell that the counter is failing. The reason is because they check the functionality, that is, they will check if the counter properly counts from 0 to 1023. So in our case, after counting 999, instead of incrementing to 1000, it is once again counting 999. So the counter is failing. Okay, so functional verification team, they can only tell that the counter is failing. Now we'll try to see what will happen if a DFT team exists. Same scenario, we will understand what will happen if a DFT team exists. Okay. So same, we are having a counter, 10-bit counter, a counter initialization and a counter observation circuit. So the scenario is, suppose counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay. So counter, suppose the counter is manufactured with a defect. So that's why after counting to 999, instead of incrementing to 1000, it incorrectly rolls back to 999. Now we'll try to understand what will happen if a DFT team exists. So if a DFT team exists, DFT patterns will be used to test the chip. If a DFT team exists, DFT patterns are used to test the chip. Now DFT, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. 100 clock pulses, range of 100 clock pulses means somewhere around 80, 90, 100, 120, etc. So DFT, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay. So if you see DFT team, we require less number of clock cycles compared to the functional verification team. So functional verification team, they are required more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we are able to tell that the counter is failing approximately in the range of 100 clock pulses. Range of 100 clock pulses is 80, 90, 100, 120 like that. So if you see, we require less number of clock pulses compared to the functional verification team. So that's why test time will be less compared to the functional verification team. Okay, test time will be less compared to functional verification team. And how we are able to tell that the counter is failing approximately in the range of 100 clock pulses itself? How we are able to tell that? It is because DFT engineers, we go for a technique called as scan insertions. So that's why we will be easily able to control and observe our circuits. Okay. So DFT team, we go for a technique called as scan insertions, because of which we will be easily able to control and observe our circuit. And we'll try to explore more on this, like how DFT engineers are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. How are we able to tell that? We will try to explore more when we do the regular course. When we go into the DFT advanced part of the training, they will be able to, when we do the scan insertion topic, you will be able to understand how DFT engineers are able to tell that the counter is failing in approximately in the range of 100 clock pulses. So DFT team, we go for scan insertion, so we are easily able to control and observe our circuit. Okay, so if you see, we require less number of clock pulses compared to functional verification team. So test time will be less compared to the functional verification team. Okay, and then DFT team will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. Okay, DFT team will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. So how we are able to tell what manufacturing defect has caused the counter to fail? It is because DFT patterns are generated using ATPG. DFT patterns, they are generated using a process called as ATPG. So ATPG tool, it actually does a process called as fault simulation to generate the test pattern. Okay, it does a process called as fault simulation in order to generate the test patterns. So as DFT patterns are generated using this fault simulation technique, okay, we will be able to tell what manufacturing defect has caused the counter to fail. Okay, so DFT team, we will be able to tell that the counter is failing. We will also be able to tell what manufacturing defect has caused the counter to fail. So how? Because DFT patterns are generated using ATPG, and ATPG tool does a technique called as fault simulation to generate the test patterns. So what is this fault simulation technique? We will understand it when we do the regular course. When we do it, you will be able to understand. So DFT tool does fault simulation to generate the test pattern. Okay. So as DFT patterns are generated using fault simulation technique, we will be able to tell what manufacturing defect has caused the counter to fail. Okay. So let's summarize the points. So conclusion is, with DFT patterns, test time will be less compared to functional patterns. So as we saw in that counter example, functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we approximately required in the range of 100 clock pulses to tell that the counter is failing. Okay. So functional verification team, they require more than 1000 clock pulses. More than 1000 clock pulses to tell that the counter is failing. DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay. So if you see, DFT team, we require significantly less number of clock cycles as compared to functional verification team. Significantly less clock cycles. Less clock cycles compared to functional verification team. Okay, so DFT team, we require significantly less clock cycles compared to functional verification team. So that is why test time will be less compared to so that is why with DFT patterns, test time will be less compared to functional patterns. Okay, so that is why with DFT patterns, test time will be less compared to functional patterns. Okay, and then DFT, we will be able to tell what manufacturing defect has caused the chip to fail. Okay, so as I discussed about DFT team, will be able to tell that the counter is failing. We will also be able to tell what manufacturing defect has caused the counter to fail. So how? Because DFT patterns, they are generated using ATPG, and ATPG tool does fault simulation to generate the test pattern. What is fault simulation? We'll discuss it in our course. Okay, so that is why DFT patterns are generated using the fault simulation technique. So that is why DFT will be able to tell what manufacturing defect has caused the chip to fail. Okay, so as DFT patterns, we are having these advantages over functional patterns. So if you see, with DFT patterns, test time is less. And with DFT patterns, we are able to tell what manufacturing defect has caused the chip to fail. So DFT patterns has these advantages over functional patterns. So that is the reason DFT patterns will be used to test the chip after manufacturing. Some functional patterns will also be used to test the chip after manufacturing, but majority DFT patterns will be used to test the chip after manufacturing. Okay, so DFT patterns has these two advantages over the functional patterns. That is, with DFT patterns, test time is less compared to functional patterns, and with DFT patterns, we are able to tell what manufacturing defect has caused the chip to fail. Okay, so as DFT patterns, it is having these advantages over functional patterns. DFT patterns will be used to test the chip after manufacturing. Some functional patterns will also be used to test the chip after manufacturing, but majority DFT patterns will be used to test the chip after manufacturing. Okay. Now, if DFT patterns are used to test the chip after manufacturing, then why do we need a functional verification team? So, any guesses? If DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team?
Functional validation is also important, right? Without verification team, how will we get to know if the chip is performing to its extent?
Yes, exactly. So, if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So, as we have exactly told, it is actually to check the functionality. So, let's consider a scenario. Let's consider an example. Say, for example, you're having a half-adder design. Sum is equal to A plus B, carry is equal to AB. This is a functional bug. Sum should have been A XORed with B, carry is AB. But by mistake, someone has written sum is equal to A plus B, carry is equal to AB. This is a functional bug. Okay, this is a functional bug. Now, for time being, just consider that you don't have a functional verification team. Okay, for time being, consider that you don't have a functional verification team. Directly, this design has got synthesized. So the design got converted into a gate level netlist, and if you see, it is a wrong design. Sum is A ORed with B. Wrong design has got synthesized. Sum A or B carry AB. So wrong design has got synthesized. And now this design is given to the DFT team. So as I told, DFT team will generate patterns just to check whether there are any manufacturing defects in each and every net of this design. Okay, DFT team, we will generate patterns just to check whether there are any manufacturing defects in each and every net of this design. Okay, so DFT team, we will generate patterns just to check whether there are any manufacturing defects in each and every net of this design. And now the chip has got manufactured and DFT patterns are applied onto the chip, and then the output of the chip, it is compared with the expected output. So input sequence is applied onto the chip, and then the output of the chip, it is compared with the expected output. Output of the chip is equal to the expected output. So which means there are no manufacturing defects. Output of the chip is equal to expected output, so no manufacturing defects are there. But whether the design will function like a half adder in this case? No, the design will not function like a half adder. Even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself is wrong. The design itself is wrong. So sum is A plus B, carry is AB. The design itself is wrong. Sum should have been A XORed with B, carry is AB. Here the design itself is wrong. Design is sum is equal to A plus B, carry is equal to AB. Design itself is wrong. So we don't have a verification team. That design only got synthesized, and that design only was given to the DFT team. And DFT team, we will generate patterns just to check whether there are any manufacturing defects in each and every net of this design. And then chip has got manufactured, so DFT patterns are applied to test the chip. So input sequence is applied onto the chip. Output of the chip is compared with the expected value. Output of the chip is equal to the expected value. It means that there are no manufacturing defects. But whether the design will function like a half adder? No. Even though there are no manufacturing defects, the circuit will not function like a half adder. The reason is the design itself was wrong. So that is what is the significance of the functional verification team. So they will be validating the functionality, whatever is written here, whether this is correct or not. Okay, whatever is written here, whether this is correct or not, that is what will be validated by the functional verification team. Okay, so now we have tried to understand what is the difference between a DFT engineer and a functional verification engineer, and why do we need both the DFT team as well as the functional verification team. We have tried to understand it. So in the next slide, we will try to understand what happens at the time of testing. So as we saw in the ASIC flow slide, this testing is done after manufacturing. Okay, so this testing is done after manufacturing, as we saw in the ASIC flow slide. Okay, we had seen it in the ASIC flow slide. So testing was actually happening after manufacturing. So testing is a process of determining whether a device is good or not. So whether our chip is good or not, whether our chip has any manufacturing defects or not. Okay. So testing includes test pattern generation, application and output evaluation. So first these test patterns. So these test patterns, it will be generated by the DFT engineer. Before manufacturing itself, we will generate these test patterns. So these test patterns, it will be consisting of the input sequence and expected output. Okay, so we have the test patterns. These test patterns will be generated by the DFT engineer. Before manufacturing itself, we will generate the test pattern. So it will be consisting of the input sequence and then the expected output. Okay, so what will happen now? The input sequence, it will be applied onto the chip. Okay, input sequence will be applied onto the chip, and then output of the chip will be compared with the expected output. Output of the chip will be compared with the expected output. So output of the chip, if it is equal to expected output, it means that the chip is good. So there are no manufacturing defects. The output of chip, if it is equal to expected output, means chip is good. There are no manufacturing defects. Output of chip, if it is not equal to the expected output, it means that the chip has failed. There are some manufacturing defects in the chip. Okay, output of the chip, if it is equal to the expected output. Okay, so here what is happening? Test patterns is there. So these test patterns is generated by the DFT engineer before manufacturing. So it consists of the input sequence and expected output. So what will happen in the time of testing? Input sequence will be applied onto the chip, and then the output of the chip will be compared with the expected output. So output of the chip, if it is equal to the expected output, it means that the chip is good. There are no manufacturing defects. Output of the chip, if it is not equal to the expected output, it means that the chip has failed. There are some manufacturing defects in the chip. Now, if a particular chip fails, okay, if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so how are we able to tell that? As I told, DFT, we will be generating the patterns using a technique called as fault simulation. So that's why if a particular pattern fails, we will be able to tell what manufacturing defect has caused the chip to fail. Okay, so if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. So what are the possible outcomes of testing? So there are four possible outcomes of testing. So one is if a good IC, if it passes the test, it is called as true pass. Good IC, if it passes the test, it is called as true pass. And then defective IC. A defective IC means it has to fail the test. Defective IC, if it fails the test, means it is true reject. Okay. Now, if suppose a defective IC, if it passes the test, it is called as test escape. It is also called as under testing. Okay, defective IC, if it passes the test. Defective IC, if it passes the test, it is called as test escape. It is also called as under testing. Okay, and then if a good IC, okay, so if a good IC, if it fails the test, it is called as yield loss. It is also called as over testing. Okay, good IC, if it fails the test, it is called as yield loss, also called as over testing. Okay, so these are the four possible outcomes of testing. And goal of good testing, it is actually to reduce the test escape and yield loss.
Yeah, ma'am, how if a defective IC passes the test, how can you identify if it is a defective IC?
Yeah, that is what we cannot identify that. So that's why goal of good testing is it is actually to reduce the test escape and yield loss.
Okay, fine. Yeah.
So yield means number of good chips divided by total number of chips. So that is what is called as yield. Number of good chips divided by total number of chips. Okay. So goal of good testing, it is actually to reduce the test escape and heat loss. And now we'll try to understand what is called as a manufacturing defects. So manufacturing defects means they are the defects that are caused by process variations and random imperfections. Okay, manufacturing defects are the defects that are caused by process variation and random imperfection. Process variation means slight variation in the transistor channel length, metal interconnect width and thickness. So all those things can impact the logical and timing performance. And random imperfection. Random imperfections means it can result in unintentional shorts, unintentional opens. So that is what is called as random imperfections. Okay. So now we'll try to understand what is the flow of DFT. So flow of DFT. So first we have the insertion phase. So insertion, we will be adding extra logic into our design, like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be adding our own test structures into the design. Okay, scan insertion, MBIST insertion, boundary scan insertion. So we'll be adding our own test structures into the design. And then we have the generation stage where the patterns will be generated. So pattern, it will be consisting of the input data and then the expected output. And afterwards, we'll be doing the validation, which is done using the simulation. We'll try to understand about each of these steps in detail in the upcoming slides. Okay, we'll just try to see the course outline. And while explaining in short what all the things will be covered in our course, we'll try to understand about each of these stages. Okay. So this is our course outline. So first we have scan insertion and next we have scan compression. Scan compression is also called as EDT insertion. So in order to achieve scan compression, if you are making use of metagraphics testing tools, then you'll be adding up a logic called as EDT. So scan compression is also called as EDT insertion. And then on-chip clock controller, ATPG automatic test pattern generation, simulations, JTAG joint test action group, memory built-in self-test MBIST, and then boundary scan. Simulations, we will be covering only the no timing simulations. So we'll be covering only the no timing simulations. Okay. The reason is in order to do timing simulation, we require a file called as the SDF file, standard delay format. So we require a file called as SDF file. Okay, standard delay format, standard delay format file. So which is not available in the test cases which is there in our institute. So that is why we will be doing only the no timing simulation. Okay, timing simulation is not covered. So if in case you want some exposure or trainings on timing simulations as well, then you can once check with the institute management if they can provide you with the training on timing simulations. Okay, so as of now in our DFT course, we will be covering only the no timing simulations. Okay, and we will also be covering IJTAG also. So we will also be covering IJTAG. So JTAG is IEEE 1149.1 standard. Okay, and IJTAG is IEEE 1687 standard. IEEE 1687 standard. So we will also be covering IJTAG in our course. The reason why I did not add it in the course overview in the demo session is because in order to understand what is IJTAG, you first need to understand completely what is called as JTAG. So that's why I have not included IJTAG in our demo session. Okay, while I'm giving an overview about these topics, I have not included IJTAG. Okay, the reason is in order to understand JTAG, you need to in order to understand IJTAG, you have to understand JTAG completely. So that's the reason why I have not included IJTAG in the demo session, but it will also be covered as but it will be covered in the regular course. IJTAG is a part of our syllabus. IEEE 1687 standard IJTAG is a part of our course curriculum. Okay. So now in the upcoming slides, we will try to understand about each topic, and we'll try to understand what is the significance of it. Okay. So maybe we can have a break for 5 minutes, and after the break, we can continue with the course overview. I'll just give you an overview about all these topics and what are all the subtopics which is covered in these topics in the next upcoming slides. So we can have a break for 5 minutes and we can continue. So now time is 3:05. We can have 3. We can have a break till 3:05 and then continue with our demo. Okay. So we'll meet at 3:05 after the group. Good afternoon, all. We will continue with our session. Am I audible? And is my voice clear?
Yes.
So let's continue with our session. So first, let us try to understand what is scan insertion. So scan insertion. So we will be so all the normal flops in the design, it will be converted into a scan flop. All the normal flops in the design will be converted into a scan flop, and these scan flops they will be stitched into a scan chip. Okay. So all the normal flops in the design, it will be converted to scan flops, and these scan flops, they will be stitched into scan chip. Okay. So now what is a scan flop? And then what is a scan flop? And what is a scan chain? What is the functionality of a scan flop? What is the functionality of the scan chain? All those things we'll try to understand when we do the regular course. So as of now, just understand that scan insertion means all the normal flops in the design will be converted to scan flops, and these scan flops, they will be stitched into scan chains. Okay. So need of scan insertion, it is actually to gain controllability and observability of the design. So need of scan insertion, it is actually to gain controllability and observability of the design. Okay. So which means in order to easily control and observe our circuit, we'll be going for scan insertions. Okay. So we'll try to understand this with the help of an example. So which means same the 10-bit counter initialization and the counter observation circuit which we discussed earlier. So counter it is failing. So after counting 999 instead of counting 1000 it again counts 999. So as we discussed earlier, how many clock pulses will be required by functional verification team and DFT team to find out that the counter is failing. So as we discussed in the previously while we were discussing, we had already discussed it, right? Functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay. So how DFT team are able to tell that the counter is failing approximately in the range of 100 clock pulses itself? How are we able to do that? So it is because we have gone for scan insertions. It is because we have gone for scan insertions. As we have gone for scan insertions, we are easily able to control and observe our circuit. Okay, as we have gone for scan insertions, we are easily able to control and observe our circuit. So that is why DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. And DFT team, we will also be able to tell what manufacturing defect has caused the counter to fail. So same points, whatever we had discussed it in the previous slide, right? Previously, before the break, we had, while understanding the differences between functional verification team and DFT team, we had taken up this example. And we saw that in that particular case, functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Whereas DFT engineers, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. So how DFT team are able to tell in such significantly less number of clock cycles as compared to the functional verification team? It is because DFT team have gone for scan insertions. So because we have gone for scan insertions only, we are easily able to control and observe our circuit. Okay, we have gone for scan insertions, so we are easily able to control and observe our circuit. So that's why DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay. So now, we will discuss about this in detail in our regular course. So when we do the scan insertion topic, we will once again take up this example and we will try to understand how DFTT are able to tell that the counter is failing approximately in the range of 100 clock pulses. How is it like that? We'll try to understand when we do the regular course. Okay. So as of now, you can just understand that DFTT, so why we are going for scan insertions? We are going for scan insertions in order to easily control and observe our circuit. So because of that only DFT team, we will be able to tell what, we are able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay. So DFT team in this example, DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So in significantly less number of clock cycles as compared to functional verification team. So significantly less number of clock cycles, compared to functional verification. Okay, significantly less number of clock cycles compared to functional verification T we require in order to tell that the counter is failing. Okay, so why? Because DFT we have gone for scan insertions, because of which we are easily able to control and observe our circuit. So that is what, in order to gain controllability and observability of the design, we will be going for scan insertion. In order to easily control and observe our circuit, we'll be going for scan insertion. So that's why DFT we are easily able to control and observe our circuit. So that's why we require significantly less number of clock cycles compared to the functional verification. Okay. Now, as a part of scan insertion topic, so what all the subtopics will be covered? Let me just tell that. So in the first class, we will be covering like what is scan cells. Okay, so in scan insertion topic, what all the topics will be covered will tell. So topic is scan insertion. This is the first topic, scan insertion. So there, the subtopics, what all the things will be covered is. So first we'll be covering what is a scan cell and then its functionality. What is a scan cell, and then what is its functionality. Same way, scan chain, and what is its functionality. Okay, what is a scan cell, its functionality, and what is a scan chain, and then its functionality will be covered. And then we will try to understand the need of scan insertion. We'll try to understand. So at that time, we will once again take this counter example. This counter example, and we will try to explore more in detail with respect to the DFT. Okay, so with respect to DFT, we'll try to explore this counter example more in detail. So at that time, we will explore more points on this. Okay, more point like explanations will be given. So as of now, I just told that DFT will be able to tell that the counter is failing approximately in the range of 100 clock pulses, right? So how it is like that? So such kind of explanations I will be giving it on the need. I'll be giving it during the need of scan insertion topic. Okay, and then so what is scan insertion? Scan insertion means a normal flop. It has to be converted to a scan flop. Scan insertion means normal flop. It has to be converted to a scan flop. So if a normal flop, if it has to be converted to a scan flop, then it has to pass certain rules. It has to pass certain rules. Okay, if a normal flop, if it has to be converted to a scan flop, then it has to pass certain rules. So those rules are only called as the scan DRCs. Those rules are called as the scan DRCs. Scan DRCs means design rule checks. DRC means design rule check. So what is scan insertion? All the normal flops, it has to be converted to scan flops and it has to be stitched into a scan chain. So if a normal flop, if it has to be converted to a scan flop, then it has to pass certain rules. So those rules are only called as the scan DRCs, design rule checks. Okay, those rules are only called as the scan DRCs, design rule checks. Okay, so in scan DRCs, you have various scan DRCs. Okay, so like clock controllability DRC, clock controllability. Okay, clock controllability DRC, and then set reset controllability DRC, set reset controllability DRC. Okay, and then potential raise DRC, and then feedback loop DRC, X source DRC, bus contention violation. Just a second, I'm just getting a call from the institute. 1 second. Okay, so let's continue. So if a normal flop, if it has to be converted to scan flop, then it has to pass certain rules. So those rules are only called as the scan DRCs, design rule checks. There will be various scan DRCs like clock controllability DRC, set reset controllability DRC, potential raise, feedback loop, X source, bus contention, like that we have various DRCs. Okay. So we will be covering about all these DRC violation and what has to be the fix. So all those things we will cover. Okay, we will cover what are all these DRC violations and what has to be its fixes. So we'll try to understand. We'll cover all these points. When we do the scan DRC stop. And the next topic will be scan chain balancing. Next topic is scan chain balancing. So scan chain balancing means keeping almost equal number of flops in the scan chains. Keeping almost equal number of flops. Almost equal number of flops in the scan chains. Okay, so scan chain balancing means keeping almost equal number of flops in the scan chains. So say for example, in one scan chain you're having 1000 flops. In scan chain 2 you're having 1000 flops. In scan chain 3 you're having 999 flops. Then if you see you're having almost equal number of flops in the scan chain. So this is what is called as balanced scan chains. Okay. So scan chain balancing means keeping almost equal number of flops in the scan chain. So in scan chain 1 you're having 1000 flops, scan chain 2 you're having 1000 flops, scan chain 3 you're having 999 flops. So you're having almost equal number of flops in the scan chain. So those are nothing but your balanced scan chains. So why do we need to go for scan chain balancing? Why scan chain balancing is required? Why do we need to keep almost equal number of flops in the scan chain? Why? So it is actually to reduce the test time. We are doing it in order to reduce the test time. We are doing it in order to reduce the test time. Okay. So how if you go for balancing, you're able to achieve reduction in test time? We'll try to understand when we do the course. Okay, when we do the course, we will try to understand what will happen if your scan chains are not balanced and what will happen if your scan chains are balanced. We will see a comparison between the two and then we will try to understand how if you go for scan chain balancing, you are able to reduce the test time, how you are able to do that. We will understand it when we do the course. Okay, so scan chain balancing means keeping almost equal number of flops in the scan chain. Like say for example, scan chain 1 and 2, you're having 1000 flops, scan chain 3, you're having 999 flops. These are balanced scan chains. You're having almost equal number of flops in the scan chain. So these are balanced scan chains. And why do we need to go for scan chain balancing? We need to go for scan chain balancing in order to reduce the test time. Okay, we are going for scan chain balancing in order to reduce the test time. And how if you go for scan chain balancing, you're able to achieve reduction in test time. We will discuss it when we do the regular course. So we'll try to understand what will happen if your scan chains are balanced, what will happen if your scan chains are not balanced, and then we'll try to understand how you're able to achieve reduction in test time if your scan chains are balanced. Okay. Now, if you want to achieve scan chain balancing, then you need to adopt certain techniques called as edge mixing and domain mixing. Okay, so in order to achieve balancing, in order to achieve balancing, we need to adopt edge mixing and domain mixing. We need to adopt edge mixing and domain mixing. Okay, so in order to achieve balancing, we need to adopt edge mixing and domain mixing. Balancing means keeping almost equal number of flops in the scan chain. So in scan chain 1 and 2 you're having 1000 flops, scan chain 3 you're having 999 flops. So in this case your scan chains are balanced because you are having almost equal number of flops in the scan chain. So we are going for balancing in order to reduce the test time. Now if you want to go for balancing, in order to achieve balancing, then you need to adopt certain techniques called as edge mixing and domain mixing. Now, what is edge mixing technique? What is domain mixing technique? And how, if you adopt edge mixing and domain mixing, you are able to achieve balanced scan chains? All those things we will discuss it when we do the scan chain balancing topic. Okay. And now, if you adopt edge mixing and domain mixing, it will again introduce some problems. If you adopt edge mixing and domain mixing, it will again introduce some problems. So that is what is problems in edge mixing and domain mixing. We'll discuss what problems edge mixing and domain mixing will introduce. What are the additional problems edge mixing and domain mixing will introduce, and what is the solution of that problem? What is the solution of that problem? We'll try to understand. So that is what is problems in edge mixing and domain mixing, and then its solution. Problems in edge mixing and domain mixing. And we'll also try to understand the solutions. Okay. So these are all the major topics which we are going to discuss it as a part of our scan insertion course. Apart from that, we will discuss some more topics like some more small topics like scan chain reordering, and then like types of scan cells, and then like scan methodologies. So likewise, some small topics also we will try to understand when we do the scan insertion topic. Okay. So these are all the major topics which will be discussed in the scan insertion topic. Okay. And next is scan compression. Scan compression means a single channel is internally divided into multiple scan chains, or else you can tell that, you can also say that internal chains are compressed into external channels. Internal chains are compressed into external channels. Into external channels. Okay. So these are your internal scan chains. These are your internal scan chains. Scan chains, we call it as the internal scan chains. So these are your internal scan chains. Scan chains only, we'll be calling it as the internal scan chains. So these are the internal scan chains. So these internal scan chains, they are compressed into external channels. Like this. These internal scan chains, they will be compressed into external channels. So this is external channel input, and this is external channel output. Okay. So these internal scan chains, they will be compressed into external channels. So this is external channel input and this is external channel. Okay. So single scan channel is internally driving multiple scan chains, or you can even say that internal chains are compressed into external channels. So the scan chains, we call it as the internal chains. So those chains, they are compressed into external channels, as you can see in the picture. So that is what is called as scan compression. And why do we need to go for scan compression? Why do we need to compress the internal chains to external channels? Why do you need to do that? So it is actually done in order to reduce test time and to reduce the test data volume. Test data volume is number of bits of patterns. Test data volume is number of bits of patterns. Okay. So scan compression means internal chains are compressed into external channels. So these are your internal chains. So these internal chains, they are compressed into external channels. Okay. So internal chains are compressed into external channels. So that is what is called as scan compression. And why do we need to go for scan compression? In order to reduce test time and also in order to reduce the test data volume. Test data volume is number of bits of patterns. Okay, test data volume is number of bits of patterns. Okay, and how? If you go for scan compression, you are able to achieve reduction in test time and you are able to achieve reduction in test data volume. How? That is what we will try to understand logically. We'll try to understand it logically. We will also try to understand with the help of formula. We will also try to understand with the help of formula. Okay. So how if you go for scan compression, you are able to achieve reduction in test time and you are able to achieve reduction in test data volume. How is it like that? We'll logically also try to understand. We will also try to take the formula for test time, formula for test data volume. We will substitute the values of the quantities which is given in the formula and we will observe what will happen with the compression and without compression. So in both the ways, logically as well as with the help of formula, we will explain how if you go for scan compression, you are able to reduce the test time and you are able to reduce the test data volume. Test data volume is nothing but the number of bits of patterns. Okay. Now, if you want to go for scan compression, you need to add up a logic. If you're working with mentor graphics tools, you need to add up a logic called as the EDT logic. You need to add up a logic called as EDT logic. Okay, to achieve scan compression. To achieve scan compression, okay, to achieve scan compression while using mentor tool, while using mentor graphics tools, what do we need to do? We need to add this logic. Add a logic called as EDT logic. The full form of EDT is embedded deterministic test. Full form of EDT is embedded deterministic deterministic embedded deterministic test. Okay. So this is what is your EDT logic. So the EDT logic, you will be having 4 components in EDT logic. So one will be the decompressor, other one will be the compressor, okay, other one will be the compressor, and then compressor, or you can even call it as the compactor. Compressor or compactor, both are same. Compressor or compactor, then controller, and then bypass. So these are the 4 components of EDT logic. So EDT logic, if to achieve scan compression while using mentor graphics tools, you will be adding up a logic called as EDT logic. EDT logic is embedded deterministic test. So inside the EDT logic, you will be having 4 components like decompressor, compressor or compactor, controller, and bypass logic. So this is what is I just shown the 2 components of EDT logic. So the decompressor and compressor. So these are your internal chains and these are your external channels. So if you see internal chains, they are compressed into external channels. These internal chains, if you see, they are compressed into these external channels. Okay. Now, if you want to achieve scan compression, then if you're working with mentor graphics tools, you'll be adding up a EDT logic. So these are the components of EDT logic. So this decompressor, compressor, controller and bypass logic is not represented here in this picture, but you'll be having the controller as well as the bypass logic. And we'll try to understand in detail about each of these components. So what is a decompressor component? What is the structure? What role it plays in scan compression? Same way, what is a compressor? What is the structure and what role it plays in compression? Same thing applies for controller as well as for the bypass logic. So for each and every component of this EDT logic, we'll try to understand what is the structure and what role it plays. Okay, what is the structure, what is the functionality, and what role it plays, we'll try to understand. Okay, so as a part of scan compression topic, so what are all the subtopics will be covered? Let me tell. So topic 2 is scan compression. Topic 2 is scan compression. Okay. So first is we'll try to understand what is scan compression, and then we'll try to understand the need of scan compression. Need of scan compression. Okay. So need of scan compression. Need of scan compression is reduction in test time and reduction in test data volume. Okay. Need of scan compression is reduction in test time, reduction in test time, and reduction in test data volume. Reduction in test data volume. Okay, so that is what. How if you go for scan compression, you are able to achieve reduction in test time and reduction in test data volume. As I explained in the previous slide, we will understand this in our regular course. When we do the DFT advanced course, we will understand it. We will understand it with the help of formula, and we will also try to understand it logically, both logically as well as with the help of a formula. We will try to understand how if you achieve scan compression, how if you go for scan compression, you are able to achieve reduction in test time and reduction in test data volume. Okay, and next is compression ratio. We'll try to understand about a quantity called as compression ratio. So compression ratio is number of internal chains, number of internal chains divided by number of external channels. This is what is the compression ratio of quantity. Number of internal chains divided by number of external channels. So this is what is the compression ratio quantity. Now, what are the points we'll discuss in this compression ratio quantity is, so we usually make sure that compression ratio doesn't exceed 100x. Okay, we usually make sure that it doesn't exceed 100x. Okay, why? Why do we need to make sure that it doesn't exceed 100x? We will try to understand. Okay, compression ratio, we usually make sure that it doesn't exceed 100x. So why? Why do we need to make sure that compression ratio doesn't exceed 100x? Why? We will try to understand that. And we'll also try to understand about the merits and demerits of high and low compression ratio. We'll try to understand the merits and demerits of high and low compression ratio. And then we will also try to understand how to decide the number of internal chains and external channels. Okay, how to decide the number of internal chains and external channels, we'll try to understand. Deciding the number of internal chains and external channels. Deciding the number of internal chains and external channels. Okay, deciding the number of internal chains and external channels, we'll try to understand. And we'll also try to understand about the EDT logic. So as I told, in order to achieve scan compression, if you're using Mentor graphics tools, you'll be adding up this logic called as the EDT logic. So inside the EDT logic, you have these components called as decompressor. One second, is my screen visible? Because my other device, it seems to be stuck. Just a second. Okay, it's visible, right? Okay. So in my other device, it was actually stuck. So that's why I just checked that. Okay. So in EDT logic, you'll be having these components, the compressor. So compressor, or else you can even call it as the compactor. Compressor or compactor, and then controller. So inside the controller logic, you will be having these mask shift register, mask hold register. So mask shift register, and then mask hold register. Okay. And then you'll be having the decoder. So in decoder, you'll be having one hot decoder, XOR decoder, one hot decoder, XOR decoder. All those things will be present. So all those things will be there inside the controller block. So mask shift register, mask hold register, decoder, that is a one hot decoder, and XOR decoder will be there. And then you'll be having the bypass logic. Then you'll be having the bypass logic. Okay. So we will understand about the structure and functionality of each of these components of the EDP logic. Okay. And we'll also try to understand some concepts like pipeline flops in compressor. Okay, we'll understand about pipeline flops in compressor, and then lockup cells in EDT. So we'll try to understand some more concepts like this. Okay. So these are all the topics which we will cover as a part of our scan compression topic. Okay. Next topic is ATPG. Full form of ATPG is automatic test pattern generation. So that is what is the full form of ATPG, automatic test pattern generation. Okay. So it is a process of generating test patterns for a given fault model. Like there will be various fault models like stuck at TDF, PDF, IDTQ, like that there will be various fault models. So ATPG, it is a process of generating test patterns for a given fault model. So during ATPG, what will happen? Test patterns will be generated. So as I told earlier, these test patterns only will be used to test the chip after manufacturing. And our test pattern should have a capability. What is the capability? So after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. So how are we sure that our test patterns will be able to detect most of the manufacturing defects? So it is because our tool does a process called as fault simulation in order to generate the test patterns. Okay. So what is ATPG? ATPG, automatic test pattern generation, as its name suggests, is a process of generating test patterns for a given fault model. There will be various fault models like stuck at TDF, PDF, IDTQ. We'll discuss about all these things. Okay. So it is a process of generating test patterns for a given fault model. So during ATPG, what will happen? Test patterns will be generated. So these test patterns will be used to test the chip after manufacturing. So as I already told in the previous slide, right? Previously, before the break, while I was explaining, I had mentioned this. Okay, so these test patterns will be used to test the chip after manufacturing. So our test patterns should be having a capability. What is the capability? After manufacturing, suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. And how are we sure that our test patterns will be able to detect most of the manufacturing defects? It is because our tool does a process called as fault simulation in order to generate the test patterns. Okay, our tool does a process called as fault simulation in order to generate the test patterns. Okay, so now ATPG is actually a very vast topic. So I'll just tell you like what all the subtopics will be covered in ATPG. Okay, so it's a very vast topic actually. So first we'll try to understand what is ATPG, and then what is fault simulation. Okay, what is ATPG? What is fault simulation? We'll try to understand. So this is these two things like fault simulation. It is actually not a very straightforward topic, and in order to understand that, it might take around 2 sessions to do it. In order to understand exactly like understand completely what is this fault, what is exactly happening in fault simulation, it might take around 2 sessions because it's not a straightforward topic. Okay, so we'll understand all these things. So what is ATPG? What is fault simulation? We'll try to understand. And then we'll try to understand like what is fault modeling, and we'll try to understand the various fault models like StuckCat, TDF, PDF, IDDQ, all those things. So this TDF and PDF is only called as the unspeed test. Okay. And we'll also try to understand about the various fault categories. Okay. Like fault dominance, fault equivalence, fault collapse. So all those things we'll try to understand. And we'll try to understand like fault classes. Fault classes. So basically like faults, they are broadly classified into testable and then untestable. Again, these untestable classes, they will be further subclassified into unused, tied, blocked, redundant, and then this testable class, they are subclassified into detected. Again, detected, they will be further subclassified into detected by simulation, detected by implication, and then like possibly detected, and then ATPG untestable. ATPG untestable is again a ATPG untestable is again a very vast thing. There will be many subclasses. There will be many subclasses of this ATPG untestable class of faults like pin constraint, cell constraint, black box, mass primary input, mass primary output, then like sequential depth, etc. Wire. So there will be various other subclasses of this ATPG untestable class of faults, and then undetected class of faults. Here I'm not having the space to write. I'm not able to write it here. I just write it. Undetected. Okay, so these are all the various subclasses. These are all the various subclasses. Yeah, we will try to understand. So this fault classes is also a very vast topic. We'll try to understand like what are each fault class, their subclasses. We'll try to understand all those things. We'll try to understand about test point insertions. Okay, what is test point insertion? Why it's required? Okay, and then pattern classification. Okay, so pattern classification, and then like fault aliasing, fault aliasing. Then we will also understand about on-chip clock controller, OCC logic, on-chip clock controller, OCC architecture. Okay, and then we'll try to understand what is called as coverage, what is test coverage, what is fault coverage, test coverage versus fault coverage, what is it? We'll try to understand. Okay, and coverage drop and coverage improvement, coverage analysis and coverage improvement, we will do it when we do the coverage analysis and coverage improvement, we will do it in the lab class. So in the theory class, we'll first try to understand what is coverage, what is the difference between test coverage and fault coverage, all those things we'll understand in the theory session. Okay, and then like methods of ways of detecting PDF faults, ways of detecting PDF faults. So one is the launch on capture, and the other one is the launch on shift. So when we discuss about that launch on shift, we'll also try to understand the pipeline scan enable architecture. Pipeline scan enable architecture. We'll try to understand what is it. Okay. We'll try to understand what is called as a death cycles. Okay. And we'll try to understand about timing exceptions like false path and multi-cycle path. Okay. So timing exceptions, we'll try to explore on timing exceptions like false path and multi-cycle path, false path and multi-cycle path. So basically, we're just going to focus on how it is taken care in StuckCAD, what will happen in TDF. That is what we are going to understand. So how these timing exceptions are taken care in stuck-at. How it is taken care in stuck-at. Taken care in stuck-at. Okay, and then what will happen in TDF? What will happen in TDF? All those things we'll try to explain. Okay. So mostly I think I have written all the topics. Okay. So this is actually a very vast topic. A2PG, it's not a very straightforward topic and it's also a very vast topic. So it will usually take around 1 to 1.5 months to complete this ATPG topic. Okay, so usually it will take around 12 sessions to complete this ATPG topic. It's a very vast topic. 10 to 12 sessions it can take in order to cover this ATPG topic. So this itself will take 2 sessions. Okay, and then this fault classes, it might take 1 session. Okay, test point insertion, yeah, this test point insertion, uh, this fault categories, fault aliasing, pattern classification, this all these things together. Okay, all these whatever I put a tick, right, that all those things together it might take like around uh, 2 sessions. Okay, and then on chip clock controller it will take 1 session. What is coverage, what is test coverage, false coverage, it will take 1 session. And in order to understand about this transition delay fault model, ways of detecting TDF, LOC, LOS, pipeline scan enable, dead cycles, all those things it can take 2 sessions. Okay, so this path delay fault model and IDDQ fault model together it can take 1 session. Okay, so this also, this one also. Okay, this is included in these 2 sessions. So totally how much session it is, Hamni? 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, around 10 sessions. And if in case like like usually it will take 10 sessions, but like some batches, if in case, as I told, this is not a straightforward topic. So if it is like if they are like if in case you are not able to, if you haven't grasped the concept quickly, then it might take it around 12 sessions as well. It depends from one batch to the other batch. Okay, so it will take around 10 to 12 sessions. So like as I told, it will take around 1.5 to 2 months to complete it. ATPG is a very vast topic. Okay, so now after that we have simulations. So simulations, it is to validate the patterns which was generated during ATPG. So which means before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. Okay, so before delivering the patterns generated during ATPG, to test the chip after manufacturing, okay, we need to validate once whether proper patterns are generated or not. We need to validate once whether proper patterns are generated or not. So this is what is called as simulations. It is actually to validate the patterns that was generated during ATPG. So before delivering the patterns generated during ATPG, to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulations. Okay. So as a part of simulation topic, we will first try to understand what exactly happens in simulation. That is, what is simulations? What is the need of simulations? Why do we need to validate the patterns that was generated during ATPG? Okay, so why do we need to validate the patterns that was generated during ATPG? So that is what is the need of simulations. We'll try to understand about the flow of simulation. We'll try to understand like what is parallel simulation, what is serial simulation. Okay, we'll try to understand what is serial and parallel simulations. Okay, so we will try to analyze it in the way we will analyze how to analyze the waveform window, analyzing the waveform window, how to analyze the waveform. Okay, so if in case your simulation fails, how to do the debug. So debugging simulation mismatches, simulation mismatch debug. So all these things will be covering it as a part of simulation topic. So simulations, so theory as well as practicals, it will be done parallelly. Theory plus practical, it will be done parallelly, done simultaneously. So the concept of simulation. So these are the points which we are going to discuss in simulation. So this is what we'll try to explain it by practically demonstrating it in the lab. So theory and practical, it will be done simultaneously. So what is simulation, need of simulation, flow of simulation, serial and parallel simulations, how to analyze waveforms, and if in case your simulation fails, how to do the debug. So all those things we'll explain it as a part of simulation topic, and at that time we'll be doing theory as well as the labs. We will explain all these concepts by practically demonstrating it in the lab. So theory and labs will be done simultaneously. Okay. And as I told, simulations, you can have two things. One is the no timing simulations. One is no timing simulations, and the other one is timing simulation. No timing simulation, and the other one is timing simulation. So in our DFT course, as of now, no timing simulation is covered. Timing simulation is not covered. Okay, the reason is in order to do timing simulation, we require HDF file, which is not available. Not available in our institute testings. So if in case you want any training on timing simulations as well, you can once check with the institute management if they can provide you some exposure on timing simulations as well. You can check with the institute management. But as of now, in our DFT course, we will be covering only the no timing simulations. Okay, if you want any exposure to timing simulations, you can once check with the institute management and check if they can provide some training on timing simulations also. As of now, only no timing simulation is covered in the course. Next, JTAG. JTAG stands for Joint Test Action Tool. So it is a IEEE 1149.1 standard. So JTAG, need of JTAG. Why do we need JTAG is in order to minimize the number of ports from the top level and also to achieve boundary scan, we'll be going for JTAG. Okay. So in order to minimize the number of ports from top level, which means what, we'll try to understand. So here if you see, I've kept a list of some important signals. So some memory bypass enable, EDT bypass enable, int mode, X mode, intel test enable, Xtel test enable, like that I have kept the list of some important signals. These are just a list of some important signals. There will be many more signals like this. Now, if all these signals are to be controlled from the top level, like if you allocate a top level port to control this memory bypass enable, one top level port to control EDT bypass enable, one top level port for int mode, X mode, intel test enable, Xtel test enable, like that, if you allocate a top level port in order to control each and every signal, then the number of top level ports, it will increase drastically. Number of top level ports will increase drastically. Okay, so these are a list of some important signals. List of some important signals. Okay, there will be many more signals like this. There will be many more signals like this. Many more signals like this. Okay, so now like this, if you control all the signals from top level, okay, if you control all the signals from the top level, all the signals from top level. Okay, so if all these signals are controlled from top level, if all these signals are controlled from top level, All these signals are controlled from top level. Like this, you are allocating a top level port in order to control memory bypass enable, one top level port for ET bypass enable, like that. If all these signals are controlled from top level, what will happen? Number of top level ports will increase drastically. Number of top level ports will increase drastically. Okay, number of top level ports will increase drastically. Okay, so that is why we use JTAG to internally control static signals. To internally control static signals. Okay, so here in this case, need of JTAG is to minimize the number of ports from top level. So here I have kept a list of some important signals. So these are a list of some important signals. There will be many more signals like these. Okay, so now if all these signals are to be controlled from top level, okay, if all these signals are to be controlled from top level, that is, if you allocate a top level port in order to control each and every signal, then what will happen? The number of top level ports will increase drastically. Number of top level ports will increase drastically. So that's why we use JTAG in order to internally control the static signals. So that's why we use JTAG to internally control the static signals. Okay. So this is one JTAG. So to minimize the number of top level ports. Other need of JTAG is to achieve boundary scan. So basically, what is boundary scan? We'll try to understand. Chip 1, chip 2, chip 3 are properly passing the test of DFT, but still the board is failing. So what it is written here is, so first what will happen is, chips will be manufactured. So first, chips will be manufactured. Okay, chips will be manufactured. Okay, and after that, what will happen? Chips will be tested on the ATE. ATE is automatic test equipment. We also call it as a tester. Chips will be tested on ATE. Tested on ATE. ATE, we also call it as the tester. Okay. So what will happen? This is how will be. This is the ATE. Okay, this is the ATE. So this is nothing but this is chip 1, chip 2, chip 3. So input of the chip will be connected to the ATE, output of the chip will be going back again to the ATE. Okay. So now here in this case, what is happening? Chip 1, chip 2, chip 3, they have passed their test on ATE. Passed their test on ATE. Okay. So as I told in the first slide, right, in the initial slides I had told, output of the chip, it is equal to the expected output. Output of chip is equal to expected output. Output of chip is equal to the expected output. So chip 1, chip 2, chip 3, they have passed their test on the ATE. So output of the chip, it is equal to the expected output. So it means chip 1, chip 2, chip 3, they are not having any manufacturing defects. Chip 1, chip 2, chip 3, they are not having any manufacturing defects. Not having any manufacturing defects. Okay. Now after this, chips will be placed on the PCB board. Chips will be placed on the PCB board. Okay. So like this. This is the PCB board. And this is like chip 1, this is chip 2, this is chip 3. So, and then these chips are placed on the board, and then the interconnection between the chips are all formed. And now what is happening? Board is tested. Board is tested. Okay, board is tested. And what is happening? Board is failed. It is failed. Board is tested and it is failed. So chip 1, chip 2, chip 3, they are not having any manufacturing defects. They are internally not having any manufacturing defects because they have already passed their test on the A. Okay, then why is the board failing? So this can be due to the manufacturing defects in the interconnection between the two chips. This can be due to the manufacturing defects in the interconnection between the chips, between the two chips. Interconnection between the two chips. So we go for boundary scan to test the interconnection between the two chips. Test the interconnection between two chips. Okay. So as a part of boundary scan topic, in boundary scan, what all the topics we'll be covering is, we will be covering about boundary scan cell, and then its structure, boundary scan cell structure. Okay, and then what are the modes of operation of boundary scan cell? Modes of operation. Modes of operation of boundary scan cell. Okay, and we'll also try to understand about these instructions like sample, preload, X test, bypass, so certain instructions. Okay, like sample, preload, X test, bypass. So those instructions. And when we try to understand about the sample, preload, X test, when we try to understand about those instructions, we will also understand how we are able to achieve boundary scan with the help of JTAG. So here in the need of JTAG, I have written it right to achieve boundary scan. So in that boundary scan topic, while we are understanding about that sample, preload, X test instruction, or when we understand, we'll be able to understand how with the help of JTAG, we are able to achieve boundary scan. Okay. And as a part of JTAG topic, what all the things we'll be covering is, we will be covering like what is the need of JTAG. So the same only, we'll cover it more in detail. Okay, to minimize the number of ports from top level and also to achieve boundary scan only, we'll cover it more in detail. Okay, and then like what is the difference between static signal and dynamic signal? We'll understand difference between static and dynamic signals. Okay, so like we use JTAG in order to internally control static signals, right? So what is the difference between static signals and dynamic signals? We'll try to understand. And we'll try to understand about the JTAG tap architecture. Okay, and then we will try to understand about JTAG controller. JTAG controller. JTAG controller is actually a 16-state FSM. We will understand about the JTAG controller, and when we are understanding about this JTAG controller, we will also simultaneously understand how with the help of JTAG you are able to minimize the number of ports from top level. How? We'll try to understand. Okay, when we are understanding about the various states of this JTAG FSM, we will simultaneously understand how with the help of JTAG you are able to minimize the number of top level ports. Okay, so like While we are understanding this, we will simultaneously we will explore how with the help of JTAG we are able to internally control the static signals. We will simultaneously explore how with the help of JTAG, okay, we are able to internally control the static signals. Able to internally control the static signals. Okay, simultaneously we will explore how with the help of JTAG we are able to internally control the static signals. Okay, and we will also understand, as I told, I have not included in the demo, but it will be covered as a part of our course. We will also be covering the IEEE 1687 standard IJTAG also. We'll also be covering IEEE 1687 standard, which is IJTAG. We'll be covering that. I have not included it in the demo because in order to understand what is IJTAG, you need to understand JTAG completely. So I haven't included in the demo presentation, but this is also a part of our course curriculum. We'll understand about IEEE 1687 standard IJTAG. So we will understand about, like we'll see a comparison between JTAG and IJTAG structures. Okay. Comparison between JTAG and IJTAG. Okay. And we'll also try to understand about the advantages of IJTAG. We'll also try to understand the advantages of IJTAG. Okay. So these are all the topics which we'll be covering it in our course. Next, MBIST. So as its name suggests, full form of MBIST is memory built-in self-test. Okay, as its name suggests, it is a MBIST technique. It is actually used to test the memories. So memory built-in self-test is MBIST. So as its name suggests, it is a technique to test the memories. We use MBIST technique to test the memories. So in our MBIST course, what we will understand is, we will try to first understand about the basics of memories. Some basics of memories, like what is RAM and ROM, what is SRAM and DRAM, like that slight basics we will just see about the memories, basics of memories, and then we will just cover basics of memory we'll cover, and then we will move to the topics which is of significance to the DFT. So we will understand about the memory fault models. Memory fault models. Like there will be various fault models like stuck at, transition fault, address decoder fault, coupling fault. Like that there will be various fault models. We will understand about them. And then memories, they will be tested using generalized algorithms. So memories, they are actually tested using generalized algorithms. Okay, so like we will understand, like we will see some basic algorithms. We'll cover some basic algorithms like 0 1 algorithm, checkerboard algorithm. Okay, and then maths plus maths plus plus march x, march c. Okay, we will cover all these algorithms. Okay, so we will, in these algorithms, what are the things we'll cover is, we'll be covering the sequence and which algorithm will be able to cover which faults in memories and how. Which algorithm will be able to cover which faults in memories. Which faults in memories and how. Okay, so these are all the things. So in memories they are actually tested using generalized algorithms. And why memories are tested using generalized algorithms also we'll be able to understand. Okay, why memories are tested with generalized algorithms also we will try to understand. And we'll take up some basic algorithms like 0, 1, checkerboard, maths plus march x march c. We'll take some algorithm and we'll try to understand what is the sequence of these algorithms and which algorithm will be able to cover which faults in memories and how. We'll try to understand. Okay. And then we will understand about test and tempest. So test and tempest means if you want to implement MBIST using test and tools. If you want to implement MBIST using test and tools, so that is what is called as test and tempest. So test and tempest, we will try to understand about the test and tempest architecture and implementation. Okay, test and tempest means if you want to achieve MBIST using test and tools, so that is what is called as test and tempest. Okay, how to how you're going to achieve MBIST using test and tools. So that is what is called as test and tempest. So as a part of test and tempest, we will be covering the test and tempest implementation and architecture. So test and tempest implementation and architecture. Okay, and then test and tempest operation protocol. Test and tempest operation protocol. Okay, so we will try to understand about all these signals like this setup, MBIST PG enable. Okay, and then go bit, done bit. So we'll try to understand about all these signals. Okay, we'll also try to understand about grouping of memories, concept of grouping of memories. Like I'll just write like group concept, step concept, all these things. Okay, group concept, step concept, all these things we'll try to understand. Okay, and also this one, memory built-in self-test. Why it is called as self-test? You'll be able to understand when we do the course. Okay, it is called as memory built-in self-test. Why is it called as self-test? You'll be able to understand when we do the course. Okay. So these are all the topics which we'll be covering it in the theory part. And in the lab part, we'll be covering IJTAG, MBIST, scan insertion. So there are basically two approaches of scan insertion. One will be the top-down approach and the other one will be the hierarchical scan. So we'll understand both these approaches. And then EDT-OCC insertion, ATPG pattern generation, ATPG and MBIST simulations. So all those things we will cover. And boundary scan also will be covering only theoretically. So boundary scan also only theory will be covered. So I think we don't have the license for boundary scan. So that's why boundary scan is so boundary scan, I think we don't have the license for boundary scan. Okay. So that's why we will be doing boundary scan only theoretically. Okay, boundary scan only theoretically we'll be doing because I think we don't have the license for boundary scan. Even this, if you want some labs on boundary scan as well, then you can once check with the institute management and check if they can provide you the trainings on boundary scan. Okay, you can once check with the institute management if they will be able to provide you the trainings on boundary scan. Okay, boundary scan labs. Okay, boundary scan as of now in our course only theoretically it will be covered because I think we don't have the license for boundary scan. So you can once check with the institute management if in case you require training on boundary scan labs, you can once check with the institute management. As of now, in our course, we will be covering only JTAG and this scan insertion. Scan insertion, there will be two approaches. One will be the top down and the other one will be the hierarchical scan. Yes, we'll be covering both the things. And then EDT OCC insertion, ATPG pattern generation, ATPG and MVIS simulations. So all these things we'll be covering it in our labs. So basically our labs, it is divided into 4 levels. So level 1, 2 and 3 and 4. Level 1, 2, 3 and 4. So level 1 and 2, they are actually like simple labs. Okay, which means like complexity will be less. So level 1 and 2 are simple labs. Simple labs. So like complexity will be less. Simple labs means like complexity will be less. So like you can have maximum of around 100 to 200 flops will be there. Maximum of around 100 to 200 flops will be there. Okay. So level 1 and 2, these are simple labs. So complexity will be less. So maximum of around 100 to 200 flops will be there. Level 3 and 4, they are designs with higher complexities. So they are actually designs with higher complexities. Designed with higher complexity. Okay. So level 3 projects, you'll be having around 4K flops. And level 4 projects, you will be having around 44K flops.
Abo.
Okay, level 3 projects, you'll be having around 4K flops. Level 4 projects, you'll be having around 44K flops. So these two are designs with higher complexities. Okay. So this will be the project work of your resume. You can mention level 3 and level 4 projects as your project work in your resume. So this will be the project work in your resume. Project work for this course. Okay, so this level 3 and level 4 projects will be the project work for your course. So they are designs with higher complexity. So level 3 projects you'll be having around 4K flops. Level 4 projects you'll be having around 44K flops. Okay. Okay. So in level 1 project, what we are going to do is we are going to have 11 test cases. So for these 11 test cases, we are going to perform the scan insertion. For these 11 test cases, we are going to perform the scan insertion. So in these 11 test cases, so 2 test cases, it will be to familiarize yourself with the flow. So this is to familiarize with the flow. Okay, so this is to familiarize with the flow. Okay, so you'll be having 11 test cases, out of which 2 test cases will be to familiarize with the flow. Okay, and you'll be having like other 9 tests. Familiarize with the flow means, say for example, you're going to perform scan insertion with the help of Tessen tools. Okay, if you're going to perform scan insertion with the help of Tessen tools means there will be a flow. Okay, so what is scan insertion? Converting normal flop with scan flops, and you need to do the scan chain stitching. Now, if you want to do it with the help of metagraphics tools, there will be certain steps which you need to follow. So that is what is the flow of scan insertion. So you'll be having setup phase. In setup phase, like you need to read the input file, library file, provide the declaration and constraint, do the elaboration, and then you have the analysis phase where DRCs will be checked. If you have any DRC violation, go back to setup phase and fix it. If you don't have any DRC violation, go to the insertion phase. In the insertion phase, only normal flops will be replaced with scan flops and scan chains will be stitched. Like that, there will be some steps. Okay, if you want to replace all the normal flop with scan flops, and if you want to do scan chain stitching, that is what is called a scan insertion. So if you want to do it with the help of tessent tools, then there will be a flow: setup phase, analysis phase, insertion phase. Like that, there will be a flow for it. So in order to first two test cases, it will actually be to familiarize yourself with that flow. Okay, and then the tool commands, tool environment, and then the visualizer, how to view the things in the visualizer. So such kind of things, in order to familiarize yourself, will be having two test cases. And the remaining nine test cases, you'll be having some DRC violations. You'll be having some DRC violations. So what are DRCs? As I told you, for normal flop, if it has to be converted to scan flop, it has to pass certain rules. So those rules are only called as DRCs. So you'll be having some DRC violations. Some rules will be violated. So that is what is called as DRC violations. You'll be having DRC violations, and we will be trying to debug the DRC violations and fix them. Okay, so in the remaining 9 test cases, we'll try to debug the DRC violations and we'll try to fix them. And basically, DRC violation fixes also, there will be like 3 methods with which you can do. One is like manually editing the netlist. Okay, one will be manually editing the netlist. Editing the netlist. Or else you can go for this create instance, delete connection, create connection. So this set of commands. Okay, or else you can go for the auto fix method. Okay, so you have these 3 methods of fixing the DRCs while working with tessent tools. So we will explore about all these 3 methods of fixing the DRC. We'll try to understand which one is more preferred and why it is more preferred. We'll try to understand. Okay, while using tessent tools, these are the 3 methods with which you can fix the DRC violations. So which method is preferred first? Which method has higher preference? So all those things. We'll try to explore it. We'll try to understand all these 3 methods with which you can fix the DRC, and we'll have a comparison between all the 3 methods. So which one is highly preferred and why it is highly preferred, like that. Okay. And next is, in level 2 projects, you'll be doing the EDT insertions. EDT insertions, nothing but scan compression. So same, you'll be inserting the EDT logic. Okay, for that you'll be having a flow. If you want to insert the EDT logic, you'll be having a flow. So what is the flow of EDT insertion? We will understand. And then we'll also analyze the reports and outputs, understand the outputs which is dumbed down. We will try to correlate whatever we have seen in the theory session, right? So we'll try to correlate and we'll see it in the lab class. Okay. And then ATPG, we are going to do the pattern generation. So we are going to generate the patterns for these fault models, like stuck at fault model, stuck at transition delay fault model, and IDDQ fault model. For these 3 fault models, we are going to generate the test patterns in our lab. And we are going to do the pattern generation with EDT as well as without EDT. With EDT and bypass patterns. We are going to do the generation. Okay, we are going to do the pattern generation with VDT as well as bypass pattern. Okay, we are going to do that. And we are going to do it for stuck at fault model, transition delay fault model, IDQ fault model. We are going to generate the test patterns. And in ATPG labs, our main aim will be on the coverage analysis and coverage improvement part. Coverage analysis and coverage improvement. So how to analyze the coverage and how you can improve the coverage. If in case your coverage is low, how you can improve the coverage. So we'll try to see that. Okay. So here also we will understand about like sequential depth concept, test point insertions. So like tessent automatic flow with which you can add the test points. Okay, so such kind of things we can see it here. Okay, the sequential depth concept, the test point insertion concept, all those things. Okay, so all these things also we will explore in our labs. Okay, so coverage improvement. So like those ones. we'll try to explore it when we do the coverage improvement topic. Okay. And simulation, as I told earlier, what theory as well as lab, it will be done simultaneously. So we'll be covering the uh, theoretical concept by practically demonstrating in the lab. So whatever earlier I have told for simulations, right? So these things, this is what will be covered. So the need of what is simulation, need of simulation, flow of simulation, serial and parallel simulation, how to analyze the waveform simulation, mismatch debug, all these topics will be covered. So theory and practicals, it will be done simultaneously. So that is what will be covered here also. And then level 3 and level 4 projects. So level 3 and level 4 projects will be doing the complete flow. So we'll be doing the complete flow, which is nothing but IJ tag and embed insertions, IJ tag insertions, embed insertion, EDT OCC insertion, synthesis, scan, ATPG and simulation. So if you just observe in level 1 and level 2 projects, we didn't have the embed insertion, IJ tag insertion, OCC insertion. All these things was not there in the level 1 and level 2 projects. Level 1 and level 2, we just did scan, EDT, ATPG and simulations. But this IJ tag insertion, embed insertion, OCC insertion, all these things, it was not there in level 1 and level 2 projects, right? But the whole flow will be covered in the level 3 and level 4 projects. We'll discuss about all the complete flow, that is IJ tag, embed insertion, EDT, OCC insertion, synthesis, scan, ATPG, everything, simulations, everything we will discuss it when we do the level 3 and level 4 projects. The entire flow will be covered. Okay. And the difference between level 3 and level 4 projects is in level 3 projects is hierarchical scan approach, level 4 projects is top-down approach. So when you go for hierarchical scan, some more additional concepts also will be coming. So like scan wrappers, okay, in test, X test, and then pattern retargeting. Okay, so all those things we will be covering it. Okay, so scan wrappers, in test, X test, pattern retargeting. So all these are some of the extra concepts which will come when we are doing the hierarchical scan concept. Okay, so that also, these are all theory topics, so we'll cover that. Okay, we'll cover these concepts as well while doing the hierarchical scan labs. Okay, the scan wrappers, in test access concept, pattern retargeting concept, all those things we will cover it by practically demonstrating it in the labs. While doing the hierarchical scan labs, we'll cover these concepts as well. Okay, so yeah. So this is it for the labs. So these are all the things we'll be covering it in our lab course. And then what are the tools used for DFT? So these are the various tools which is available in the market. In our course, we'll be making use of the mentor graphics tools. So for embed insertion, we'll be making use of test and embed. For scan, we'll be making use of test and scan, scan compression, test and test compress, ATPG also test and test compress, simulation Questa sim. So at one point, we'll be running the synthesis. So synthesis alone, we'll be making use of design compiler, which is the synopsis tool. Rest of the other things we'll be doing the course. Rest of the other topics will be explaining the labs with the help of meta graphics tools. Okay. And yeah.
Ma'am, 12 axis will be
So
having
some
24/7 or how is it?
yes, tool access will be 24/7.
Yeah, okay, okay. Thank you.
And some more extra topics apart from what is there in the syllabus, some more extra topics also I'll be covering it. So let me just give you the list of some extra topics which I will be covering it, which is not actually there in the syllabus, but I will be covering some extra topics. I'll give you an idea about some extra topics. So these topics which was asked in the previous batches of students, so I just want to, I'll just cover it up for your batch as well. Okay, so some extra topics. So previous batch students had requested it. So I had covered it for them. So likewise, I'll just give you an overview about these topics as well. So apart from what is covered in the syllabus, these extra topics I'll be covering it. So I'll be giving you an overview about these topics. Previous batches of students, some students they would have requested, so I would have covered it for their batch. So that is what I'll just give you an overview for other batches also, for your batch also. So IEEE 1500 standard, okay, IEEE 1500 standard, RAM sequential, and then ROM embed, okay, and then K rules, F rules, and then what else? Logic based. So all these points, these are some of the extra topics which is not there in our course. But previous batch students had requested, so I'll just cover it for your batch. So I'll give you an overview about these topics as well. Okay, and then I will also cover STA. STA overview also I will give. STA is static timing analysis. So it is not a DFT topic. Okay, but some interviewers they expect you to know some basics of static timing analysis. So what is asked in a DFT interview, like what is setup time, what is hold time, what is setup and hold violation, what are the fixes, how to find out the maximum frequency of operations, or such kind of points, whatever is asked in the DFT interview. So those kind of questions I will cover in the STA topic. Okay, and basically like this course you will be having like first DFT basics will be covered, basics course you'll be having. So basics course, so it will go for around 2.5 months, 2 to 2.5 months it will go. So like what are the things will be covered in this courses? GVIM, GVIM is a text editor, so we'll be covering that, and then digital design, and then like Linux, Pickle, CMOS, okay, Verilog, all these topics will be covered. And next you will be having the DFT advanced course. So DFT advanced course, it will go for around 3.5 months. 3.5 months or 4 months. It depends. Some batches we can complete it in 3.5 months. Some batches it will go for 4 months. Okay. So all the topics what I had told in the previous slides. Okay, all the topics discussed in the previous slides, that is was the course curriculum. All the topics discussed in previous slides. Okay, so this is what is your course curriculum. Okay, and who can attend this course? So any student who is in the final semester seeking DFT as their course curriculum. Okay, a new college graduate who is from relevant branches of engineering and science. Lecturers or professionals if you want to switch your career into real-time industry experience, or working professionals with similar or other VLSI domains. Like you're from physical design, but you want to shift to DFT means you can shift that. Okay, or else you're working in IT, but you want to shift to DFT means VLSI means you can attend this course. Okay, so placement support. We are having tie-up with various VLSI companies. So like students are entitled to placement support based on their performance in the course assignment. So during the course, we'll be conducting some assignments, we'll be giving some assignments, presentation sessions, tests, mock interviews, all those things will be conducted. So based on your performance in those things, you'll be given the placement opportunities. And then mock interviews will also be conducted so that you will gain a confidence face the regular interviews, original interviews, and previous interview questions and preparations. So, like previous companies, previous batch students, they would have attended the interviews. Say they would have faced some questions, some application oriented questions, all those things they would have faced. So, those questions, a collection of those application oriented questions along with answers. So, I will discuss it as a part of your course. Okay, previous batches, previous batch students would have faced some application oriented interview questions in their interviews, right? So the list of those questions I'm having, so I will discuss those questions along with the answers as well. Okay, and we'll also share like what are the previous companies, what are all the questions the other students have faced. So those kind of details also we will share it with you. Okay, and application oriented interview questions which the other students have faced, previous batch students have faced. So we will explain the concept. We will explain the answer in the class. We'll take the question as well as the answer also. We'll explain it in the class so that you can tackle similar kind of questions in the interviews. So that is it. Like if you have any queries, you can ask.
Ma'am, from when does our regular classes commence?
Can you check that with Manohar sir? I will share with you his number. One second, I'll share the contact
Okay,
details. You can check with the
okay,
respective faculty. One second.
okay. Thank you.
Uh,
Ma'am, I can know your background, like where are you from? What is your name? Sorry, we never had a formal introduction.
yeah, my name is Vidisha. So I have been working here for around 3.5 months, 3.5 years. And I have a training experience like around 15 batches of DFT training I have given. I've also trained company freshers from Juntron. I have trained them, and then some companies like Intel Malaysia. I have given a 6 months training on this DFT course curriculum. I've also given week-long workshops for certain companies, corporate trainings like L&T and Bell. And currently, I'm also currently giving a corporate training for Bell candidates, a 3 months course.
Good to know, ma'am. Thank you.
So let me share the contact details. One second. Okay. So this is Manohar sir's number. So you can contact sir for schedule and then tool related queries. Okay. So the course starting or end dates. Just a second. And then this is Manohar sir's number. Sorry, second, I'll share it to everyone. This is Manohar sir's number. So regarding schedule, tool related queries, course starting and end dates. So you can check with sir. And then any queries related to fees, you can contact Usha ma'am. So let me share her number. Second. This is Usha ma'am. So course related queries, sorry, fees related queries, fees related queries. You can check with Usha ma'am. And then anything related to placements, you can check with Webhouse sir. One second, I'll share with you his number. So this is Webhouse sir's number. So any placement related queries, placement related queries. or any course related queries. So as I told, right, if you want some exposure on timing simulations as well, I just check. I just asked you to check with the institute management, right? You can check these kind of queries with web browser. Okay, so as I told, like timing simulations is not covered in our course, and boundary scan labs is not covered in our course. So if in case you want to check if that is feasible to cover it, if in case you require any trainings on that, and if you want to check if it is feasible for the institute to provide that training, then you can check those kind of queries to web browser. Okay, regarding placement queries or course related queries, you can contact web browser. If an individual group is created, you can directly post the questions in that individual group. So, like there will be a group with your VLSI Guru ID and your name. If that group is there, means you can directly post the questions in that group, or else you can contact them individually, or else you can also contact in the number which is available in the institute website. Okay, you can also contact them through the number which is available in the institute website. Okay, so one second, I'll just check if I have given the if I've typed the numbers correctly. Yes, okay. Yeah, you can contact them, and also like I think all the queries I just posted it there to whom you can contact. If an individual group is created, you can directly post in that group, or else you can even contact in the number which is there in the institute website. Okay, so yeah, any other questions you have?
Yeah, ma'am. Before joining the course, any prerequisite or anything we need to start learning for basics?
No, the DFT basics, so it will be all the prerequisites will be covered during the basic training itself, like
Okay.
GVM, digital design, then electrical, CMOS, everything will be covered in the basic course. So in the basic part of the training.
Okay.
Okay. So do you have any other queries?
No, ma'am.
No. Then thank you all. We will end today's class. So you can just uh, note down their numbers. I'll just end this meeting in another 1 minute. You can, in the meantime, you can just take a picture of their numbers.
Ma'am, what will be the timings of the course, ma'am? Weekends?
Like it actually differs from one batch to the other batch. So that also you can like check that with Manohar sir. So it will differ from one batch to the other. So like timing, schedule, all those things you can check that with Manohar sir.
I understood.
So thank you all. We will end today's class.
Thank you, ma'am.